So one of the lessons that we're going to go through today is we're going to cover how to convert from one type of connector. So in this case, it's an IEC 62196 type 2, which is physically a little bit larger and wider. It's kind of a European standard for a type 2 charger. And instead of instead, a lot of the Type 2 chargers in America use a little bit different format, and that would be what is more commonly recognized as the Type 2 charger. Make sure I've got both actual images here because I've got looks like duplicates. But what we have, yeah. So let's download that, and then there we go. So the more common type that's a round plug that's a little bit smaller than this is an SAE, and it's a J1722. So we're going to look at the technical drawings for both of those, and we're going to recreate some of those components. So one of the first things that we want to do is take some measurements of a physical object. So this is going to be general to basically anything that you guys are going to be doing as far as measuring physical objects. You can get yourself an inexpensive set of dial calipers. I recommend metric because frankly, you guys don't know what 376th of an inch is, and neither do I. And so we probably shouldn't use this system at all. And so I know a lot of people are hung up on freedom units. They just waste time and don't actually help. The metric system is a lot easier to use, and there's a whole lot of reasons why. So some of the key dimensions that we need are the inside dimensions. So an approximate diameter, but this has kind of a D shape to it. So what we're trying to figure out is roughly if this interior is the same as the spec for just a plug-in socket as a holder design. So I've included in the attachments for this week two different drawings, and we'll go over those in a little bit. But this is the starting point. And what you're going to do is with calipers, you're going to measure using the backside. So this is a really important exercise because you guys are going to be doing a physical device. You're going to be recreating something. And so I posted some instructions also in the announcements. And you're going to be recreating to physical accuracy your water bottle, your travel mug, your something like that. You're going to include a picture of that object. Then you're going to include a bunch of your measurements and things like that. So it's helpful to have like a scratch sheet of paper that you write stuff down on. So in this case, I'm going to use the inside ears for my calipers. And what we're doing is we're going to take a couple different kinds of measurements. So one is going to be finding using those ears. We're going to be finding the inside diameter. And so we're going to expand it out until we can't go any farther. And what we're trying to do is figure out the widest point. So you kind of move it up and down until you get to the widest point and it's stuck. And then you bring it out and take a measurement. So in this case, we have right at 64 millimeters ID. Calipers you can get a hold of on eBay pretty easily. You can get them at some other stores. You can buy them on Amazon. I would avoid like some of the Harbor Freight shops and things like that. They're okay, but I picked up these. These are Mitutoyo, which are Japanese. Literally, people put men on the moon using like Mitutoyo calipers and slide rules. Okay, so if they're good enough to get men on the moon with aluminum foil and rubber bands, for crying out loud, they're plenty good enough for your SolidWorks class. Like seriously. I really like these. These give both SAE and metric measurements, and the graduations are listed in, for this specific model, the graduations are listed in thousandths. And so it will measure either thousandths of an inch or thousandths of a millimeter. which is really, really handy. And that really helps. But yeah, I definitely would recommend getting an example of this. I'm going to show you using just a common tape measure if that's all you've got for now. I'm going to show you the same thing. But you're trying to find that widest spot, and you're trying to use that thumb screw to adjust it outwards. So you're kind of trying to slide it up and down to get the widest possible area. And so now 64 millimeter is the ID. So we'll compare that to what we have for our drawing. And this one, it's going to be a little bit fuzzy to see, but we'll do our best here. They have, yeah, they have a couple pieces to this housing. So I'll kind of explain what this looks like. So we're going to be examining this a little bit more closely, but it's this same D shape. And so, yes, I could just do something like find this kind of housing on Amazon and purchase it and not go through all this work. But since I'm teaching a SolidWorks class and I actually build stuff and use real tools, we can show an example of how to build a real object that has practical utility and actually does a thing. It serves a function. So this is the interior that goes inside the plug, and then the plug itself goes into this sleeve so that it's locked in and protected from moisture intrusion and all kinds of other stuff. So our housing here is actually sized for theoretically the outside dimensions. So what this interior diameter is, so the symbol representing that is a circle with a line all the way through it. So you'll see this on a bunch of different kinds of drawings. This is the one that we're paying attention to. So right here, this leader line to this dimension is 64 millimeters exactly. So 64 millimeters. The good news is that means it is to spec, which is really, really helpful. So 64 millimeter ID, and it has a flattened off top here. And so from the center line to the top is about 25.1 millimeters. And so measuring that on the caliper is going to be tricky, but not impossible. So I'll show you quickly how that actually looks. So the center line on this one, another reason why I chose this particular design is all the way across, you get a consistent horizontal line at the threads. And so you have a meaningful reference point, and you want to measure from that line, that imaginary line between those mounting holes. You want to measure from that imaginary line up to the top. And so on this one, you can sort of see, I'll see if I can get the light to catch it just right. Yeah, there we go. You can see there's two print lines. So those are meant to be basically a friction fit against the top of the housing of that charger. So those two are going to be important in our design, but we're not going to pay as much attention to those exactly because they're protruding about a millimeter or so. They're not a huge part of our design until we get to some of the later steps. But we want to measure up to the very top surface. So the top surface, not to one of these interior lines. We actually want to measure to one of the top surfaces. So to estimate that, you're going to line up with that imaginary line. So again, you're going to be using the interior ears of your caliper. These teeth are for the outer diameters. These are for inside dimensions, outside dimensions. And that's your rule of thumb for using calipers. So you line up one edge right on the top. So right on the top, and then you bring up the other side until it becomes even I'll use a reference point here until that line lines up with your imaginary value. So I have right here, if those are actually at center line, let's see. If those are actually at center line, you're gonna have to kind of do a judgment based on the top view. And yeah, that looks right about right. So what we measured, or what we have on our drawing, is 25.1, and looking at it at kind of an angle so that I can visualize what that plane or that center line would be. I measure right at like 25 millimeters exactly. And so that tells me that exterior housing is exactly to spec. And so if I had one of those type connectors, it would be a very snug fit in here, and it would be a secure hold. So the good news is that means it's to spec. So in this case, where it's a circle with a flat cutoff, that's the spec that we're trying to pay attention to for some of the detail, is from this center line where I have mounting holes on the sides. From this center line measuring up to the top side is exactly 25.1. So this is very, very important to know. Okay, so we know that this is to spec. We know that the housing actually matches this IEC 62196-2 spec. So we know that this end is correct. So now we need to design the adapter that goes in between, right? Because the majority of the level 2 chargers here, commonly in cars, are going to be, and this one is a lot more clear, which is great. At least a little bit more clear. This is the SAE J1772. So this is a connector type that you may have seen in a couple different varieties. SAE J1772. So you guys have probably seen these types. It's helpful to see some of the examples. Tesla has their own type. Most cars, most electric plugins here in the US are running this style 1772 for AC, and then they have a DC variant that is being used for some of the fast charging and stuff like that. So you're going to have that component, and the top side of the connector is exactly the same between those because they're the same spec. It just may or may not have the DC fast charging connector piece attached to it. So both of these are variations of that 1772 spec. This one is the European spec, and these aren't necessarily exactly to scale. Japan also uses the 1772 spec, but they use some different things for the Chinese market and things like that. So you guys have seen a variation. These are what the majority of the chargers you'll see in the US. For anything that isn't like a really crazy all electric, anything on Amazon or whatever is going to be the same sort of idea. And what we're trying to recreate is something like this. This is Newark. They're a really good supplier for electronics and parts. So this is what the back end of that connector would look like. So we're trying to recreate that socket, but do it as an adapter. So that's what we're going to be working on, is how to adapt this to that European style. So here's what we're going to need. We're going to need to start a new part. And what that's going to allow us to do is that's going to allow us to bring in the key dimensions. So we know what our outer dimensions are. That's the 64 with that 25.1 flat top cutoff. So we're going to recreate that shape first, as our outer sort of receiver shape. And then we're going to work on the interior portion of that. So I'm going to pull this up on the other screen as a reference. What we can do with this is we're going to start a new sketch. And we'll do this front plane, keep things pretty simple. So we're going to start with a circle because that's going to be our effective base geometry. We'll set up a quick smart dimension on this because we know our outer diameter is 64 millimeter. Then we have a flat top. And so in this one, yeah, what I'm going to do is I'm going to make a center line reference. We're going to use a couple center line references, and I'll show you what to do with them. There's a lot of ways that we can actually make use of these, but I want to get you guys in the habit of starting to add center lines for things. We could draw half of this part and do mirroring and some other things. We'll work on those efficiencies later. For now, what we're going to do is keep a center line so that we know how to keep both of our designs centered. So this spacing between these two needs to match that 25.1 millimeters. And so in mine, it actually seemed to be a little bit closer to 25 millimeter exactly. So I'm going to go based on the actual part that came off the printer, because there might be a lot of times there's as much as about 100 microns or 0.1 millimeter variance on things. And so what this does is this means I can now connect with the I can connect with the top of the circle. And so I can now delete the top part of the arch because this is the actual shape of the receiver, right? So these could be filleted just slightly, and I probably will do that a little bit to do a sketch fillet just slightly. I'm thinking the radius of these, it's pretty short. I'm going to go ahead and include the ridges for placement as well, but these are really more like about 5 millimeter radii, maybe. Pretty small, but it's going to keep some of the material from getting caught up inside the corner. What this will also do is this will give us a little flexibility in some of the design parameters. Okay, so from that outside edge, actually, you know what? Before we do that, we're going to want to use those corners as reference for dimensions. So what we're trying to do is measure the dimensions between the corner piece, so right where the sharp corner happens, and where the ridge begins. So we're trying to measure this interior piece right here. And that one, because of clearance issues, we won't be able to get an exact measurement from the ID. So we'll have to approximate it using the OD measurement technique. And that's going to mean lining it up as best you can on a straight plane. And that looks to be from the corner. It looks to be separated by about 5 millimeters from the very edge of that corner. And they are indeed, these are 3 millimeters wide. Okay. So 3 millimeter wide, and they're about 5 millimeters in. So we're going to represent those with small corner rectangles. We're going to zoom in here and represent them. So these are inset by about 5 millimeters. They are 3 millimeters wide. And I'm going to say they are about 2 millimeters deep, just to give plenty of clearance for these. So this is where, especially starting to use center lines, there's a couple disciplines you can start to learn here. So we'll go ahead and make use of some of that symmetry. So instead of going in and recreating, let me switch back to screen share, because that will be helpful. Otherwise, you'll get super lost super fast. Sorry about that. Always be sure to ask questions and bring up issues. We're going to delete this second rectangle. I'm going to wipe out that second rectangle. I'll recreate the dimensions so that you can see the measurement. There we go. So I'm going to actually come back in and do a center line. So we'll start learning how to take advantage of summary of symmetry in our process here. So I have two indentions, and these are spaced in from the corners by about 5 millimeters, and they are 3 millimeters wide. To give myself just a little clearance, I'm going to do 3.2 millimeters, and then they're 2 millimeters deep. So what I can then do is take advantage of the mirror entities about this line, mirror about the center line, and then recreate it on the other side so that I'm not doing tons and tons and tons of work. I'm doing half the work of the drawing. And what you can even do is you can do that at the end. So I could come in and do a power trim. I don't usually do this one because it's sort of like taking a katana to your drawing. And if you have too much caffeine that day, it can really make a mess of things. So you just draw and cut through everything you don't need. So when we're done ninja slashing, we go back to trim to closest. So the next time we don't ninja slash our entire drawing up. Then I can come in and I can trim out this top section of the box. And so now I have half of my drawing for the receiver side of things. And that will really, really help. Another thing that I'll do for the sake of getting myself some actual clearance is I'm going to do 63.8 millimeters in actual diameter here, to give myself a couple hundred microns of clearance distance. That's going to help account for problems with tolerance. So that will give me a pretty good range. Okay, so now we're going to go back and take elements of this 1772 spec and take this exterior, and we're going to figure out how we can drop that inside of this area. So there's a portion on the bottom that's like a locator key and then a clip at the top. So we have to account for all of that. And this is part of the reason why we need all this information. So they give us a couple different radii, which are really important. They give us the outer diameter and then inner diameter. So in this case, 44.2 millimeters is our inner diameter, and that's the big thing. So that's our base circle that we're going to play around with in the spacing. So when you're trying to make some kind of an adapter, it's helpful to have that. So for this, instead of doing an inner circle, I'm going to do a center point arc. And I'm going to start with, I'm going to start actually intentionally not near the center point and not near the origin here. I'm actually going to drop this down in between somewhere on the center line so that it doesn't associate with one of those other points, so that I can move it later. So I'm going to set up this radius, and it's going to be 180 degrees. So now I've got to size it. So again, our OD there based on the drawing is 44.2. So you can see kind of the circle with the line through the center, 44.2. So half of that. So 44.2 divided by 2. So now we can see we actually have some room to play around with. And what this also means is I can now set a custom distance. So I can set a wall thickness. As a general rule of thumb for prints, I like to have somewhere on the order of about 3 millimeters or so of wall thickness on a part if I'm going to be using it in practical terms. That just helps to make life a little bit easier. And so what we'll do is we'll adjust the arc down once we get our second circle accounted for. And so that's this one for this locator pin. This locator tab has a radius, an inside radius of 26 or 25.6. And so that's really, really important. So 25.6 is our next key dimension. So I'm going to go back and do another center point arc. I'm going to attach it concentric with this circle. And I'd love to make this particular feature a little bigger for you guys, but it's just not practical. So 26.4. And I'm going to have a sweep of a certain length. So we're going to get our dimensions. So this is 25.6. So I'm going to update that. So 25.6 radius, 25.6. Okay. 25.6, and the width of that is also important. So we need to know something about that. The width has to be about 8.5 millimeters. So here from center line to the edge needs to be, I'm going to give it again another about 200 microns of clearance. So I need 100 microns or 0.1 millimeter of additional spacing. So instead of 8.5 divided by 2, I'm going to do, you can even write it basically as a formula, but I'm going to do one of the steps at the same time. So I'm going to do 8.5 plus 0.2, which is 8.7 divided by 2 to give me the additional clearance. And so 4.35. And then this has a line going straight up to connect the two together. All right, so this piece of the arc we don't actually need. And now we can kind of get a sense of what our spacing can actually be. So what I'm going to do is we've got a good amount of clearance up here at the moment. But you're going to see where we're going to have to make some adjustments at the top. So I'm going to set a distance here where I actually want a distance between these two arcs. Yeah, and it's going to be the same as the center to center distance. I want to try and maintain, in this case, I'm going to cut it down to about 1.5 millimeters. Actually, I'm going to increase that because I've got to go the opposite direction. So 3.5 millimeters. is going to give me a little bit of a thin spot at the base, but I'm okay with that because I have more material. And I can actually, because of the way this adapter is going to go in, I can actually technically go all the way down since I have additional material underneath. I can basically zero out that dimension. And so this is part of what you can look at as you're thinking your way through stuff. So bring this down to about 4. 5 millimeters. There we go. So I can virtually eliminate that distance. This leaves just enough material to kind of barely tie the base together when we go to do this. This is part of the reason why you want to lay stuff out in drawing format like this, because you can get a pretty good idea what the dimensional differences are. So at the top, we have a couple more things that we have to account for that particular plug. Again, because of just the shape of these, you're going to have this intrusion at the top, regardless of what the design looks like. You're going to be in that zone. So you need to account for that additional spacing, and that's what those last couple of dimensions are here. So those are about the exterior, and they don't actually give a lot of detail about those. They're about the same width here. And so one of the things that you often have to do is kind of calibrate based on other dimensions. So once you start adding these in, this has a wall thickness that is about 6.2. Let's see. So about 6.2 millimeters on either side, which is again about 3 millimeters. So that's that 3 millimeter wall thickness that I'm talking about for parts. It's just a rule of thumb. You want somewhere on the order of 3 millimeters of material in order for it to be strong enough to do the job reasonably, because material stuff you guys will learn later. So 3 millimeter wall thickness means 8.5 plus the 3 on either side. So this is a little bit bigger than something like this circle that has a total diameter of 12 millimeter. You can see this is definitely larger. So 8.5 plus 6 is on the order of 14 millimeters or so, which is really kind of the minimum cutout for this. So we could do about a 15 millimeter cutout at the top. The next thing is going to be figuring out what that height is. So that looks to be on the order of, using again this top reference point, that looks to be on the order of, because they're almost even here, you're easily about 8 to 9 millimeters here total, because you're about a third of the way, another third of the way, another third of the way would be about 9 millimeters in total thickness. So we're going to do about 9 millimeters clearance at least for the top. And I'll probably still have to do some modification at the very, very end. But 15 millimeters wide and 9 millimeters tall from the top of this circle is what we're looking at. So that is a rectangular cutout that's going to be of a certain size. I'm not going to associate it with any of these other dimensions. So this needs to be, nope. This needs to be, as a minimum, about 9 millimeters tall. It actually probably needs to be more than that. So I'm going to have to make a slight cut into the top of that housing, which is kind of what I expected, but it helps to lay it out in terms of the drawing. So that height as a minimum in terms of like the latch mechanism, there needs to be an open an open slot because I think this is going to be a reasonable friction fit. So I don't think we need to have the ability to actually have it clip in necessarily. But you can see how close we are at the top here. So I might have to play around with that with the actual real device and see how far off we are. And right at about 7.5 millimeters. Then we can make a connection here as a vertical line. And we can cut out these other pieces that we aren't going to need anymore. So the top part of this arc and that open space. And up here, because this is going to be a space that's basically cut out of our design, what we're going to end up doing is we're going to end up trimming all of those. So this I'm going to fill back in with a line all the way across. And what that's going to do effectively is, actually, I don't even have to fill that in technically because it's going to need to be open anyway for this particular design. So I'm going to close this in down here at the very bottom and connect those 2 points. And now I have a fully enclosed area. So by spending the time doing that work, what I can do is I can now pick this whole entity, copy it about the center line, and I have one continuous object that I can now recreate as an adapter for this, which is really kind of handy. So the total depth of this, to take that depth measurement with calipers, that's another thing that you guys have almost certainly never seen. So we're taking our flat plane of this, and at one of the edges, we're going to rest the base because there's a piece. Let's see if I can convince it. There we go. So there's a piece that actually protrudes from the bottom. That's a depth finder. And what that does is allows you to, if you're sitting square on the housing, so especially sitting across the very corner there is a very stable reference point. You can drop the depth finder down to the base and figure out exactly how deep this goes. So right at 40 millimeters total depth, which should be about right. So 40 millimeters in total depth gets us what our extrusion depth needs to be. So here we go, extrusion, and we can take both of those regions and we're going to do 40 millimeters. And there we have designed an adapter to go from one holder spec type to another. So I'm going to save this. It's another thing I want you guys to start getting in the habit of for a whole lot of reasons. Save early, save often. SolidWorks will crash on you. If it hasn't happened already, it will, probably with increasing regularity. The newer versions are supposed to be better about that, but stuff happens and SolidWorks crashes. So it just is what it is. So this is a J1772 adapter. All right. So I'm going to take that part and actually recreate the real part from this and start putting it into service. But that's a quick example of how to take an actual physical object and recreate it with some very specific, very real dimensions. I'm also going to do just a little bit of not actually filleting, but chamfering at the base. Um, and nowhere near 10 millimeters. I really only want about 2 millimeters, 45 degrees. So maybe even 1 millimeter at 45 degrees is going to give some additional clearance. So I'm going to go ahead and include that. No, not the last face. Delete that. This is why you want to be real careful with the components you select. So what that's going to do is allow for a little bit easier placement of that insert. So by chamfering the edge in terms of practical purposes, that's going to allow for a little easier time fitting things. And I can do the same thing with these edges where I can do, I can actually do, again, not a fillet. I'm actually going to do a proper chamfer on these. No, not the face. That'll give me some additional clearance on each of those as I go to set those into place so that everything should be able to slide in to place very nicely and give me a friction fit sufficient where I can add some adhesive and then not have to worry about anything coming loose and creating other issues. So the top doesn't necessarily need a ton, but I would probably do, I will actually do a fillet here at the top, and it's going to be nowhere near, I'm going to do a 1 millimeter fillet for that edge and this edge, as well as the front edges here and here. And those will physically be represented on the actual part. Those will work pretty nicely. I'm actually going to go up to 2 millimeters on those, just to make it a little slightly nicer aesthetically. And that will give us, that will make it a little bit slightly more sort of self-locating in a way. And so that'll really help with making things work more like how they are supposed to. All right. So this one's done. Now we're going to create another object. And so we're going to do, let's see. We're not going to do any screw thread patterns, but we're going to do some more with revolve and sweep in terms of physical object design. So I'm going to close this. I'm going to start another part. And what this is going to do is we're going to take, again, some more key dimensions and we're going to recreate a physical object. So this is probably actually a really good example because there's a lot of specific dimensions and you'll be able to see it maybe a little bit more readily for what we're trying to do. So I will screen share. I'll stop the screen share here in just a second. So there's going to be two parts that we're going to need to create for this. And that's actually going to be really, really helpful. So I'll see if I can kick up the light source a bit and make your life a little easier in terms of visibility, because I think that'll help. All right. So what this is going to do is be an example of a container like you might be using for your create a physical object from or create a drawing from a 3D physical object. So what we're going to do is we're going to take some key measurements. This one is a simple cylinder, but also not a simple cylinder. So first thing is tell me how we can recreate the how can we recreate this object best? What's the single best feature? So look around in the features tab. What's the single best feature we can use to recreate this? Because that's something that we really want to make sure we've got. Is we want to make sure that we've got our yeah, exactly. We want to use our revolve base boss, because we're going to see some differences in a couple of the features. So this isn't just a smooth cylinder. This actually has a couple points where um, they widened the mold, so that as these are going down the assembly line, those two high and low spots at the very top and bottom. And I don't know that you'll actually be able to see it on camera, so you'll see it when we go to do the drawing. Maybe I can get it to fake out a little bit there. Um, those act as, on the assembly line itself, those act as rollers to keep anything from scuffing the stickers and the marketing and the branding of the actual device. So they act as rollers on the assembly line. So they actually serve a purpose. They're the kind of feature that we need to include in our physical object recreation, right? Because just doing a cylinder that's then narrowed at the top and then open in the center is not actually the correct way to represent this. So we get a couple of key measurements. So one of those that we need to know is going to be our wall thickness. So wall thickness, and this one reads right at 1.2 millimeters. So it's not a super thick wall, which we wouldn't expect. This is has a couple kind of interesting features in terms of the geometry of the base. So we're going to have to recreate that. So I'll show you how to do some measurements there when we get there. But we're going to start by the base cylinder itself. And so what is the total exterior diameter, right? For calipers on objects that are like much, much larger, a lot of times you can't get them down far enough. And so you'll only be able to get them, something like this, where you can't get them, you just don't have the reach, or there's an object or handle in the way or something. So at that point, you have to sometimes kind of take it to the end of the cylinder. And so instead of trying to get it to reach, sometimes you can get it to the end of the cylinder, but most calipers are only sized for somewhere around about 6-inch diameter max. So anything bigger than that, you're typically using other stuff. But you can use the same properties, the same principles when you go to physically measure your object, right? Most of you will be able to find a tape measure or something like that. You can even, print tape measures online. There's a lot of options for how to do that. One of the other things that you want to keep in mind, if a tape measure is all you've got access to, is the end actually has some slop in it. Anyone know why tape measures have slop in the end offhand? Because I mean, measuring distances, that's a pretty important thing, right? So why does that move around? Because it moves around almost like, I don't know, maybe like a 16th of an inch, right? So does that mean tape measures are just inaccurate, or is there a reason those are that way? What do you guys think? Good guess. Good guess. Anyone else have a reason they think this is? So material expansion, it's a reasonable guess. It's a lot more simple probably than anything you've ever been told. It's because sometimes you're trying to measure stuff to the inside, sometimes you're trying to measure stuff to the outside. So if you need the outside dimension, you have to hook it onto something. And what it's doing is it's accounting for the thickness of the end of the tape measure. That's what that slop is. So it's counting for the actual thickness of this dimension. And that's why a lot of times people that are inexperienced, when they go to do something like cut flooring, they cut it twice and it's still too short. That's because a lot of times they're not actually measuring correctly. So it pulls out to add a 1/16 of an inch thickness in terms of actual dimensions. And then when you go to measure the inside, so you try and put it up against the baseboard or the edge of something, it'll contract to eliminate the thickness of that lip, that hook, so that you're not accounting for that in your measurements. So that's why tape measures actually move. These are important things to know about your measurement tools in case this is all you've got access to, so that if you're measuring on the inside, be sure to push that in to get the most accurate possible dimensions, right? So the interior diameter, as near as I can figure it, is about, it's right at about 2¼ inches. It's right on that zone. The exterior, you have to again pull and make sure that's taut. The exterior is right at about 2 and what is that? 2 and I guess that's about 7. Yeah, that's 2 7/16. Yeah, right at 2 7/16. So this is part of the reason why using a tape measure and not having calipers is going to possibly take you a lot longer, and it's going to be a little bit more challenging, but it is doable. So you can get there. You can estimate the diameter, but especially for things like a cylinder, it's really hard to estimate the diameter sort of accurately. Sometimes you can cheat and they'll have mold lines like this one does. So you can measure right along those mold lines and get an idea. And so this exterior is just 1/16 over 2½ inches. So that is 2 9/16. So again, trying to type all of that in, figure out dimensions, get yourself a metric caliper and save yourself a lot of heartache throughout all of your engineering career. It'll be a whole lot better for everybody. So 2 and that fraction would work out to about 5 point. Let's see if I'm still calibrated on the 0. Yeah, I'm still calibrated. Okay. So 2.552, 2.552, no, 2.554 for our outer diameter actual. Yeah. So just shy of 2.56 inches, which is frustrating kind of a fraction. So that gives us an idea for our rectangle. We also need to know height, and this is where a lot of times your caliper is going to be severely limiting, because you can't actually measure the entire height with the caliper no matter how much you try, and that obviously is a frustrating reality. So you need to have a couple different varieties of things. You can measure up to a certain point, and that's what you do in this case. So if you're trying to work with a measurement tool, something like that, you would go up to the edge of the sticker or some hard boundary that you can measure against. And this would be 150 millimeters plus, and then you would drop it down to measure from the edge of the sticker up to the top. So you're gonna have to line that up as best you can. You wanna make sure to use one eye, not two eyes, so you don't suffer from parallax issues. So that's right at 3 centimeters, so 30 millimeters. So 180 millimeters total. And that's probably exactly what the height is. So 180 millimeters, we go to start drawing that. And what we're going to do is, again, start learning how to reference We're going to change our view so that we have everything square as we're trying to recreate detail. I'm going to add a center line. I'm going to make it a little bit tall. You can start with a rectangle as the base shape. So we know this whole thing in total has to be 180 millimeters tall. We know that our outer radius, our effective radius, is the outer diameter divided by 2. So 64 millimeters, so 32 millimeters is our width. We're going to do some fine filleting and some other sketch elements and things in here as we get some more of the detail. But this will give us the starting point. Then we need our base. So here again, we need our base. So you're going to have to grab the very top where you're not into the threads and kind of biasing your results. It's right at 60 millimeters. So another reason why I would argue that actually this was designed in metric. And we're going to do another one here for the top. And we're going to say this dimension is 30 exactly. So 60 millimeter OD. And then what we can do is make a connection between these two lines. And we can cut away the part we don't need up here and here. Yes, even though those have reference points. And we don't need that. We don't need this small segment. And we don't need this small segment. We can connect that with a single point. But we actually don't even need to, and you'll see kind of why that is later. But we're going to use some of the reference. So we added, let me go back a couple steps. So that you guys can see. So we added a rectangle. We sized it correctly for 30 millimeters to this edge. Added a line across connecting, cut away the parts that we don't need using our trim tool again. So our trim entities. And we actually cut out a couple of these points as well to replace it with just a single line segment to make life a little easier later. We'll find out why. So now we have an important part of our base. We are going to add in a couple of these other features, including we now need to figure out what these ridges are for the top and the bottom that act like the wheels to keep these rolling without scratching or scarring or marring the marketing materials. All stuff that engineers have to take into account that marketing folks never have to think about. Is how to protect all of that silly work so that when it gets to the end destination, it's still a good looking product. So we have to take another couple of measurements, one of which is going to be the height or the thickness of these. So you're going to measure the thickness, and again, you can use it just as easily with a tape measure, except you're going to have to do more fractions and decimals and all of those sorts of things. So in that case, it's going to be a little hard to actually take that measurement with the end. So instead, you want to line up something like the 1. So you're going to be You'll need to take a look on your screen. You may have to pin it. I'll try and make sure that it's pinned. But you might want to line it up against the 1 or something like that, so that you're not trying to actually measure against the end, because you won't be able to see the markings very clearly. So if I were to line it up, for instance, with the 2 at the top, I can see that that's exactly 1/8 of an inch thick, or thereabout. Or I can measure with calipers and determine that this is right at about 3 millimeters. So there's that 3 millimeter number again. It's going to come up a lot. So we actually have a 3-point arc that we're going to do for this. So it's going to be 3 millimeters in height, and then it's going to be about 1 millimeter in depth. So we're going to do some smart dimensioning. So let's go back to this. So we do a 3-point arc, and we're going to do our smart dimensioning. So start at the top, second point here, and our radius, yeah, about 2 millimeters is about right. And our overall height here is right at 3 millimeters. So yeah, this is about right. What this is also something that we're going to recreate at the bottom. So it's going to be a radius of about 2. So let's do 2 even. There we go. So radius of 2, an overall section width of 3. So that's also going to be down here at the base, except the base isn't square. And that's one of the things that we've got to really pay attention to. So we've got one more thing that we've got to measure. What that means is you've got an inner circle diameter. And we need to know what that is. So this diameter, and you can also, again, use the mold marks as a reference point. So that inner circle diameter is about 48 millimeters. So 48 millimeters in diameter. So we need to add another, we're going to add a rectangle only because this is going to make a little easier reference point. So this dimension is 48 divided by 2, or 24 millimeters. And then we're going to have a roll off. These can be a little bit tricky to measure. So I'm going to show you what we did on the screen here, because we're going to have to go back and forth a little bit. This is the kind of the hard part about this format. So we added a rectangle that has the outer diameter of this inner circle. It's actually going to be an arch, and we're going to roll this in to an arch coming up into the center. So we'll cover that here shortly, because this is a part of the injection molding process for these. And what this will do is we now have to measure where our radius is and what that radius looks like. So we've talked about them, but in order to measure that radius, you need to be able to, something like a caliper is really, really, really going to help, because you want to be able to know how far, and a lot of times it's going to be easier to use the ID, because what you can do is you can line it up against the very edge. And so this is going to be a frustrating camera trick here. You're going to line up the ID against that edge, and where one of the teeth is going to touch right where that curve starts, and one of the teeth is going to be flush with the top. So this is on this side of the radius. This has a radius of right at 6 millimeters. If you do the same thing for the base, right where that radius starts to roll, this one looks like it happens to be a symmetric right at 6 millimeters. So that's what we're going to do, is we're going to do a 6 millimeter fillet at this corner, 6 millimeter symmetric. All right, so now we have our corner of our bottle represented. And the reason we needed to know this is that ridge starts right at the top of that radius. You can kind of see it there. I'll have to disable some of the settings. This is why I'd love to be able to use the other streaming setup. So I may do that here with some of the future classes. I may be able to use the other studio, which will be great. So that ridge is up about maybe 3 millimeters or so from the top. Yeah, from the top of that ridge is about 4 millimeters. So about 4 millimeters up, we have an arch. So I'm going to do a 3-point arc. All right, we're going to set dimensions. So first one is this dimension is about 3 millimeters up. The radius is 2, and the height difference is, or that width is about 3 millimeters. So then you'll see we have both of our ridge lines set up. We can also use our trim entities tool to come back in here and cut. And what this will do is this will now set up the exterior of our dimensions here. And then we're going to use another feature that we've kind of looked at, but we haven't really maximized it yet. So we'll do, so we'll go back over here. So I'll walk through that quickly again. So we have our radius of curvature at the base. We have our curve that we've added in. So this is that rolling edge at the edge of our container. So 2 millimeter diameter, 3 millimeter width again. So the same as up above here. So we've got our 2 millimeter diameter, we have our 3 millimeter. Curious. Okay, those are at the same point. What we are then going to do is we're going to take advantage of what's called an inset. So once we finish down here at the base, we're going to do an inset. So here, one of the other things that we know is the actual, we know this height. You don't want to grab center points of stuff. It just creates heartache. So let me undo the dimensions selected here. Escape key is your friend on all the things. Okay. Smart dimension every once in a while goes stupid, just does dumb things. So this is right at about 1.5 millimeter thickness. And then we're going to round this over into an edge for another 3-point arc to recreate the base geometry of this. So we basically need a depth measurement, and this one happens to have a diameter. So I'll show you the couple quick measurements I'm referencing real quick. So there's a flattened spot at the center. So we're going to get the approximate ID of that. It's not going to be exact, but it's going to be pretty close. So this is right at about 15 millimeters on average. So it's about 15, and we need to know the depth of this. So 15 millimeter diameter at a depth of, and in order to measure a depth for something like this, you have to be looking plainly across you have to look across the plane of this. You can also use another flat edge or another flat edged surface as a reference tool, and then subtract differences. You can get a pretty close eyeball approximation if you're looking flat across the plane of it. So the camera is looking right now flat across the plane of that. So if I look flat across the plane, I can line up the base with the horizon, and I know exactly what my depth is, which is right at 5 millimeters exactly. So 5 millimeters gives me what I need to set this. So I'm going to do another quick rectangle here. And so it's going to be 5 millimeters in depth from this edge, so the very base to here, it's going to be 5 millimeters. And then this diameter is going to be 15 divided by 2. So there is my other corner. The reason I'm using a rectangle as a reference is there's my other corner, so that I can then do a 3-point arch. And I actually need about 1.5 millimeters or so there. So I'll have to set that up. And we want the arch to be kind of a smooth, continuous line. So now we're going to come in and trim some of the entities we don't need anymore. Get rid of some of the extra. Okay, so that's gone. That's gone. This part is gone. This part's gone. That point is probably okay. This is gone. So now we're left with this. And as we trim out some of these things, we come in and do a sketch fillet, especially for these corners. So this one is actually a 1 millimeter fillet, which is about right. So there's this kind of rounded base that then swoops up into, I'm going to see if I can get it to convince. Nope, it's not going to let me do another fillet there. But anyway, what that does is that gives me the base for the object. Now, what can be really tricky is we want to take this object and create a wall thickness from it. So we're actually going to trim these extra pieces that we don't need. So there's another line there we don't need. All right, so that one's gone. What we're going to do is, by eliminating these, we actually get the opportunity to do an inset. I'm going to cut this one out actually as well. What we're going to do is we're going to get an opportunity to do an inset. And so this is a feature you haven't seen, called an offset entities. So we're done with our trimming. We're going to use an offset entities, and that wall thickness was about 1.5 millimeters. The reason we needed that is we need to come in here, and all along this line, what it's going to do is follow the trajectory sort of as best it can and recreate as many of these features as it can, So again, these are really huge time-saving tools. And that offset entities is going to allow us to get close enough. I'm not going to worry about the specific detail, like does it actually jut in right here? Probably not. That's not a level of detail that I'm interested in right now. But I am interested in capturing all of the major physical features of this object. So 1.5 millimeter wall gives me the things that I need. So I'm going to come in with a line tool, add a line to close up here. And again, same up at the top. And now I should have theoretically an enclosed area. What I may do is I may go ahead and sort of reposition. I may reposition some of these. I may not. I'm going to see what it looks like. Yeah, see, some of those should be okay because it's not a fully defined sketch. If I start moving stuff around, it's going to create much heartache and consternation, and I don't really want to do that. So what I'm going to do instead is add one last thing, because one of the things that we're still missing is our threads at the top. So we have threading at the side, and the way to capture this in a simple manner, there is another thread tool that we'll learn about later, but they have a couple different features. So one is just a ridge line at the base of this, and so that's a very simple tapered shape. So we take the measurements on what is the thickness, so right at 1.5 millimeters, and the height up from this neck, the height is 4 millimeters. So 4 millimeters up, 1.5 millimeters total thickness. We're going to add that. We're going to add that right here to our lid. So we add a simple rectangle. There we go. We add a simple rectangle. And we set dimensions. So it's 1.5 thick and 3 millimeters up from this ridge. And then we have a couple more of those. Really, we have one more of those recreated. It's a little bit more of a triangular shape for the thread. And so we're just going to represent that simply. And I'm going to measure that here. So it's going to be about the same 1.5 millimeter width. It's going to be, we're going to take a measurement somewhere along that distance. So that's going to be right at about 4 millimeters up again. Four millimeters up again. And this one, however, is going to be slightly tapered. So we can do that a couple different ways. I'm going to do it here in the sketch. And just with freestyle lines. I know approximately what the angles are of these. So these angles are about 30 degrees. This one needs to go the opposite direction, where it's going to be minus 30 degrees. And that total height from edge to edge is going to be 1.5 millimeters. There we go. And so right at 30 degrees is very much exact to what you see on the threads of a bottle. They're going to be very triangular in shape. A lot of times this top piece is rounded or filleted. And so here we have our two other remaining features, and we're going to trim out the last remainder here. Okay, we're going to trim out our last remainder. Okay, so what this will do now is this will represent our entire geometry, and we're going to call this sketch done for now, because I'm not going to go through all of the time, energy, and effort of trying to make this a fully defined sketch, because that will take time that we just really don't have. So we're going to come back up to the features. We're going to do a revolve. We're going to take that region. I'm actually going to get in here and grab the contour itself. Or this region, not the actual contour, so not the lines themselves. And then I'm going to pick the axis of revolution and hit OK. And what you can see is we actually now have something very representative. We're going to add the material real quick. So this material is technically a polyethylene. So it's polyethylene terephthalate. Hopefully you guys remember that. That's one that is pretty important. So if it's a clear material, this is what it is. So polyethylene terephthalate. I don't know if they have a really good appearance for this. Teflon, polyethylene, nylons and Delrin's ABS. So they've got a few different options. You just want to make sure when you're picking one that it has a mass density. So we can apply this and close. So this one doesn't happen to be clear. What we can do is edit the actual appearance. And we can give it the appearance of like clear glass, and that will represent this material pretty well. So we've got PET and the appearance of clear glass as if it were a clear bottle. And we can see that we've actually recreated this with a very high degree of accuracy and fidelity. So all the way down to the injection mold features. These are those ridge lines that I was talking about, that as the bottle sort of spins or rolls down the conveyor belt, it spins on those two, almost like these are wheels, and there's an axle connecting them so that they don't scuff up the stickers as they're rolling down that geometry, or as they're rolling down that assembly line. So questions on this, because I know there was a lot of steps there. So what questions do you guys have before we keep going? Because that was a lot of techniques all at the same time, and that's part of the reason why I'm recording lessons for you guys, is an attempt to try and help you guys be able to keep up by going back and reviewing multiple times. Or do you guys have this all makes sense, and you're ready to now make the lid? See, if you don't ask questions, it becomes really hard to answer them. So that's the next thing. And I know there's like a little bit of a delay. So I'll give you a couple minutes to catch your breath, type up a question or two. Then we'll recreate the lid. So I'll go ahead and save this as container. But this is exactly what I'm looking for in terms of the physical object assignment. So the complexity of the object doesn't necessarily matter so much as the fidelity of your recreation. So if I were to take an image of if I were to take an image of this container and then put that in my report right next to this drawing, I would go, yeah, you've absolutely captured the detail that is there, right? So it's not about picking something that's harder and more detailed necessarily, but most things that you're going to come across are not just going to be an extruded cylinder and then you're done. And that's really the important thing to represent. So yes, you can use a travel mug. Yes, you can use a Nalgene bottle. The techniques that we've gone over today are very applicable to those. Almost all travel mugs have different levels and layers and features. So this one has kind of curvature at the top, has a huge transition step at the base, and then has another inset with another rounded transition, and then flares back out and is rounded and filleted at the base. And then the base itself just has an indent, and it's smooth at the bottom, but not all of them are smooth. So those are the kinds of details that I'm looking for you guys to pick up, and start learning, how do I recreate a complete physical object? Because if I were to, for instance, 3D print this object, because of the dimensional fidelity that we're using, if I were to 3D print this object, it would be able to work. I would sort of be able to snap on the lid. It would be compatible. I would be able to hold the same sorts of things, but because it doesn't actually have a thread exactly, that's just a cheap way to represent the threading. It would sort of kind of fit in place, but there's a little bit more to it than that. The key is I want you guys to start learning how to recreate with very, very high fidelity. So yeah, for something like a bottle that has a straw, you want to try and recreate that as well. So you'll assume that the straw is completely vertical, and you'll want to try and recapture dimensions. It doesn't have to be a mug with a lid, but you want to have like a couple different images of the physical part or the physical specimen that you're recreating, so that way, what you can do is you can work from that measured geometry to a finished product. So that's kind of the key, one of the key parameters there that you want to pay attention to. So it's about trying to recreate with very high fidelity. So other questions? And then we'll show how to recreate the lid as well, so that you guys will see how to do that. So this one, I'm going to go ahead and save real quick. So this is all right, so this is ball container PET, and then we'll recreate. So the next piece that we'll recreate is the lid for it. So what this will do is give you the other side of what you're looking for. This is going to be really pretty straightforward, but there is some additional detail that we need to pay attention to. So it's not just an extrude part. There is kind of a cool feature that we can use, so I'll go ahead and demo that. You can try and add some measurements. I will get a good sense from the pictures that you take of the approximate scale of what the object is. So if you draw a water bottle that's 3,000 millimeters long, I'm probably going to call you on dimensional inaccuracy, because if you have a water bottle that's that long, we need to reinvestigate how to measure stuff. So we'll cross that bridge when we come to it. Hopefully we don't have to come to that specific bridge, but we want to learn how to measure and measure accurately. So this has a thickness of right at 11 and a half, almost exactly. Yeah, 11 and a half millimeters thick. And then our inner diameter is measured again by kind of sliding this back and forth and then finding a good a place where it's at the widest point. That inner is 63 millimeters. So we'll start a new part for this. So we'll start a new part for this. And our base is going to be that 63 millimeter. So in this one, we're going to do the top plane just to be a little bit different. So we're going to start at the origin, and this is going to be 63 millimeter. But in order to use this cute feature, we're actually going to look at the outside diameter. So I'm going to measure to the outside, right at, yeah, 64 and a half, which makes sense. 64 and a half millimeters is our outer diameter. And then we're going to extrude that to a thickness of 16, 17. Yeah, right at 17 millimeters. So we're going to extrude that, and then we're going to use another feature that you guys maybe haven't seen yet. So 17 millimeters. All right, and hit OK. So we're going to come up here and we're going to use what's called the shell, which you can use, but you have to use very, very carefully. So we're going to set our dimensions first. And the object we're going to do is we're going to create a shell for this whole entity. And we really need to see the preview. The trick is we need, this is going to create a shell on the inside. The trick is, and we can technically do a shell outward, and that is maybe a little bit easier in this regard. So this one, I think, will give us what we're actually looking for if I do it this way. So let's see. I think this will give us, yeah, this will give us what we're looking for. So the shell in one step, I'll show you a couple different variations of this because it's not going to be obvious to you guys. If you just shell the whole thing, what you end up with is this. That doesn't really help. You can change the view type to be a wireframe and see that on the inside, and we can actually do a section view too to see what this actually looks like. So a section view shows us what this actually looks like on the inside. So yes, it created a shell of the object, but it created a shell of the whole object. So what we needed to do was we needed to exclude. So I'm going to hit the X to get out of the section view. We needed to exclude one of those top planes by selecting it. And what that means is you're going all the way up to that face with the shell. So similarly, if we had done the top face and the bottom face, this will create a hollow ring, which is not helpful for this specific instance, but can be later. So it's a tool you can put in your tool bag for use later to save you a little bit of time and effort. If you eliminated, just so that you can see for the doubting Thomases in the room, if you try and do just that exterior face, it's like, I have literally no concept of what you're actually asking me to do. So that won't help you. But if you shell all the way up to that face, you end up with this this final part. So there we go. So we've got our selection. I'm going to edit this so that we don't have, since we created that error, it redid things and stuff. So we quickly created the shell with the 1.5 millimeter thickness. Now what we're going to have to do is we're going to have to create the threads on the inside, and we're going to use the same sort of technique, the same size for the thread pattern. There is an actual tool that we can use to make spiraling threads. It's called the spiral tool, strangely enough. But we're going to have to do another couple things. So we've got most of what we need here, but we need to add another sketch. And we need to do this on a right plane and then reset our view so that we know where we're drawing. So in this, we have a starting rectangle that we're going to use as a reference point. So we need this to be 1.5 millimeters. And what that's going to do is give us a reference point for where to put the threads. We're going to do the same measurement as far as the approximate depth. This one is not nearly going to be quite as deep, and we're going to be right at about 7 millimeters in depth. So 7 millimeters in depth. We're going to add a rectangle here, and it's really only one thread that goes in. So we're going to use our smart dimension. We're going to say this distance needs to be 7 millimeters. This distance needs to be, we said in total width, it's about 3 millimeters. And then about a 30-degree angle, height wise, what's our height? Right at 1.5. And our lines so that we can recreate that angle. So these are going to be a little bit different in terms of their overall dimensions. This one's going to be slightly different. I think this is too high. It has to be closer to about 2.5. There we go. So about 2.5 millimeters. So these threads are slightly different in overall dimensions, but the depth is going to be the same. So we're going to cut out the parts we don't need. And then we're actually going to do a revolve of this thread itself on the inside of the object. So we're not going to cut away this centerpiece. We're going to leave it in place. And we're actually going to set a center line, or we can actually use another reference geometry that we don't have opportunity to very often. So I'm going to add that. I'm going to include what's called an axis. So what this does is you select the interior of a cylinder, and it will create an axis along the center. So it's kind of like a center line, but it can be referenced always from everything else throughout the rest of your time drawing. So it's actually very useful. So we're going to go back to our features, and we're going to do our revolve. And we're going to revolve this region specifically, but we're going to revolve it around our axis instead. So this is another way to use this same technique. And now we have our thread represented in our in our geometry here. So a lot of really cool things that we can do with that kind of technique. There's a lot of really complex features that we can replicate, and that actually gives us just about all of the detail that we need. We also have a fillet at the very top, and so it's not 10 millimeters. It's very much a 1 millimeter fillet, so this is a smooth top. So now what we have is a smooth top and our thread recreated here. And we can now change our material. So we can specify edit material. So this one doesn't actually have a material listed, but it's going to be probably from the same pot of material. So it's also going to be PET or the polyethylene terephthalate under plastics. Apply, close. Then we're going to change our appearance to be a little bit more reasonable. So this one happens to be a satin blue. It's really kind of a light blue, but this is SolidWorks. We can't expect, all that much cooperation. Yeah, they really don't have a lot of good options. So blue satin plastic is going to be as close as we can reasonably get, but that's pretty close. So now one of the cool things that we can do when we have two different part files is we can actually put them together, and you'll see some examples of how some of those work. But this will give us, I'll show you that real quick just so that you can see what it looks like to put together an assembly. We're going to get there later in the semester, but I want you guys to be aware of these tools and have some opportunities to practice them. So we're going to save this. For each instance of that, you're going to need to save parts. So this is ball container lid, ball lid, PET. So this is fairly straightforward. You guys have stumbled upon the make drawing. You haven't really seen the make assembly from a part yet, but this is what that looks like, just so that you can see. I'm not going to expect you guys to know all of everything, but you have to click somewhere to bring in the first part. Then you have to insert components again, bring in the lid, and that brings the lid in. You click somewhere in the field. We'll learn about mates later in the semester. You're going to do a couple different kinds very frequently. So here I'm just going to do concentric to the exterior, and I'm going to make them anti-parallel because I'm cheating. So I'm going to add that one, and then I'm going to add a separation distance of 1 millimeter from this interior face to this top face. And let's see, that goes down not far enough. So we have to go 1 millimeter. We have to go up about 3 millimeters. Oh, we have to flip the direction. That's why. Flip the direction. So right at about 3 millimeters, we're going to do 4 millimeters just so that we have a little bit of actual separation. And there we go. So our lid and our finished part, our lid and our clear PET container actually fit together nicely. So this is how you put together an assembly of what you're working on. We'll go into a lot more detail for mates and stuff later. this is just a way to put together something quickly, concentric, and then separation mating allow for quickly putting together something like container and lid combos. But all that geometry is now recreated in careful detail, and that's the kinds of things that I'm looking for you guys to get to, recreating curvatures on parts of handles and getting everything as exact as you can, because that gets you more and more and more experienced for how to actually make some of these things work. So there's a lot of cool stuff that you can do. So I'll go ahead and close this because we'll do more on assemblies later. So I don't need to save this because I don't need that. All right. So final check-in for other questions on techniques. I know there's one more that we're going to kind of try and do a quick demo on because of some of the things that are coming. So we've talked about revolves and sweeps. We've done kind of a number of different fillets now. We've talked about what you guys need to do in terms of 3D models from physical objects. We're going to start learning more about what we demoed today, about how to do 2D technical drawings and turn those into 3D, getting into lofts and some other stuff. So there will be some really cool stuff we can do with lofts as far as techniques. But sweeps are really powerful. So any questions on things like the fillets and sweeps, probably it would be helpful, since some of you haven't seen it yet, to go over some drawings. So maybe let's do that while you guys are typing up questions. And that will help to kind of keep things rolling along, because we've still got a lot to cover in terms of techniques before you guys are ready to just start drilling and drilling and drilling on parts. Because the more practice you guys get, the better off you'll be. So once we're in an object, creating the drawings, what you're going to want to do is you're going to want to make sure you've saved your part, saved it with a name that you can find it again, saved it somewhere that you can find it again. And under file, you're going to go make drawing from part. So you've probably seen reference to this in the tutorials. A lot of times somewhere like A3 ISO is a reasonable starting point. And what you'll see on the right side is you'll see some different view options, and you want to include several of these. We're going to get to a point where one of the exercises that I think we're going to do is you guys are going to create a part, make a drawing from it, and then you're going to swap those drawings around. And from there, you'll be able to start recreating a part from somebody else, and you'll have to go back to them and go, wait, what did you mean by this dimension? Or wait, I don't know what that is. Just so that you get a sense of exactly what's really needed for all of these. So isometric views are really helpful. There is another couple things. So when you guys are drawing parts, this is a really helpful thing to include in your assignment so that I can see exactly what dimensions. So like Miss Pac-Man, that was a really helpful thing to include, etc. So you're not doing drawing really necessarily on these, but you're looking at the drawing tab. And so standard 3 view is a really good starting point. So you'll select the part that you want, and you click somewhere in, you double click on the part. That's what it is. So you double click on the part, and this gives you, you can kind of shift these around. You're going to see that they're tied together in terms of the way these lines are drawn. You want to leave yourself some room to get into some detail. So going back to our reference drawings from today, because we really use reference drawings. As soon as it'll actually bring it up, maybe it won't. There we go. So again, different views so that you can get an idea of exactly what the part is. So for instance, like the depth on this particular part is 30 millimeters, even though the depth on the other part is about 40 millimeters. So um, these are really helpful things to know and understand about this. But one of the things that we can do is make sure um, that we create drawings that mean something, drawings that give you enough views so that you understand what it is that you're working with. So you start adding annotations to those by so once you've got your key views, for something like a bottle, the two side views are not, like a front view and a side view are basically the same thing, right? But you can also bring up the view palette over here, and you almost always want to include an isometric somewhere in there so that you can include and see what all is actually going on in terms of detail. And then under annotation, you can use smart dimension and start getting information like, hey, what is the height of this? What is the overall exterior? So let's see. Select the two outer boundaries, and you got to make sure smart dimension is still selected, because SolidWorks, sometimes it will give you what you're looking for there, sometimes it will not. So depending on what you've got, there we go. Sometimes you have to just change the view to get the specific dimension that you're looking for. So 64. And then this will also help kind of train you to pay attention to some of the interior features. You can get some of the information like, hey, what's the thickness? So what's the shell thickness there? What's the inner radius? So the true radius. And you'll also start to see some of these different symbols showing up, like, hey, this is a diameter. Hey, this is R, this is a radius. Heights of things. Some of these features you're not going to be able to get a really good measurement on from this angle. You would have to include something like a bottom view, but you can still get some of the same information based on this. So, and how far that arch goes at the base, 45 millimeter diameter, outer diameter. So this is going to give you all these different diameters, but you have to make sure that it's in a way that you can actually see, because there's so many different ones. It's really hard to tell what's actual. So there's your 64 diameter, but this tells you about that exterior ridge that's about 65 millimeter diameter. And then you get some detail about the radius of 2, right? You get some detail about, so this one did a circle. That's not quite what I'm looking for. I'm actually looking for the thickness. So I got to measure it here. So 1.5. And then same kind of thing. I want to measure from that point to that point, 1.5 again. So what these will do is give you some of the kinds of detail that you need to get from one point to another. So back to smart dimension. Sometimes it'll deselect the tool for you. 3, and then 4. So this is why you kind of have to play around. You can especially drag these out to give yourself some more space to work with, and bring these down below or something. Like, there's a lot of ways to rearrange the drawing in a way that makes sense, that'll tell me, oh yeah, okay, you recreated the key pieces of information, right? So like this has a radius of 6, right? This has a thickness of 3. Um, all of those sorts of things give me a really good sense of what the dimensions are. Maybe coming down here and getting the diameter for this guy, 48 millimeters, right? Um, these are the helpful things. So it's going to give you access on the drawing to stuff that's external in the view, not stuff that's internal. So that's some of the details that you want to try and capture when you're measuring some of these, create a drawing from it and include that in your assignment, because what that's going to do is give me a better sense of, yeah, you know exactly what you're looking for and why. If you know those things, then you're probably getting the right kinds of detail put into your drawing. So those are things that I need to see that you guys are understanding. All right, so questions on drawings? I know you've had kind of a little bit of an introduction to those. Hopefully this will be helpful going back in and seeing in more detail, but any other questions on that? I know you guys are back to reaching kind of the microwaved oatmeal phase. So I'm probably going to wrap it up here for today because we've covered enough techniques. We've got a few more that we're going to drill on pretty intensively here next week, but we're going to finish up the last of our kind of intro techniques as we get into lofting and some of the more complicated stuff. There's a lot of really interesting geometries that you can develop with those very quickly, so they're very cool. This week's video is going to be going up shortly. I'm going to try and make sure that gets up today because I'm going to be doing some business travel here during the rest of the week. So things are going to get a little chaotic for me, but I'll try and keep an eye on messages as I'm able to. So this will go up today as soon as it gets done being encoded. Last week's video should be up, should be posted. I'll try and make sure that that's the case. We've got a couple other things going on too. So I'll go ahead and stop the recording there since we're going to be wrapping up. So yeah, make sure a lot of the pieces, that's actually a really good question. Before I close that down, a lot of the pieces that you're looking for in SolidWorks, what you're going to do is you're going to go to whether in PC or Mac, you're going to follow basically the same process. C drive or your main drive, users, and public. What you're going to find under public documents is a SolidWorks folder. And so SolidWorks 23 samples. This has a bunch of things, including the examples for the tutorials. So the keyway piece is actually going to be here in this particular folder. So you can search under these. There's examples of motion studies and molds and all kinds of stuff, fillet components, a lot of stuff is in here. So public users, SolidWorks, or public users, public documents, SolidWorks is where you're going to find a lot of stuff and things under the samples and under tutorials. So a lot of things that you'll be able to get a sense of. So lots of pieces and components for large scale assemblies. A lot of those things are all here. So yeah, a lot of cool stuff that's in there that you guys need to know where it is. So the real objects assignment, it's going to be most helpful to have a drawing, have a couple pictures of the actual physical object, give me some dimensions, and then draw up the actual part in SolidWorks, pick a material, and then try and pick an appearance that gets you as close to the object as reasonably possible, and then show things like the mass so that I can get an idea. You know, if you have a 12 kilogram bottle, probably not accurate unless it's actually made of extruded lead. it's probably not 12 kilograms. But I want to see how you guys are doing these and what kinds of features you're using to recreate the geometries that you're seeing. So those are the things that are really, really important. All right. Any other questions?
Do you want it like a PDF or do you want it like you have it on the screen, like draw it up like that?
The I want it in like a uh, PDF format when you're all done is a really good idea. It can be a Word doc or a PDF. That'll have like some images from the part. You'll have your screenshots from SolidWorks, and then your drawing format, because that'll help me to know exactly what you're doing, exactly what you're working on. And then in regards to Discord, I'm trying to get to that this week. I just haven't found a lot of extra time for some of those kinds of tasks. So I'm going to try and get to that this week, and get that up, and I'll post that in the announcements when it's up. So, um, any other final questions? All right. So I'll go ahead and stop recording there.